Good morning everyone. So, in today's lecture I am going to talk about the different special cases of Euler-Lagrange equations. So, just a brief recap, in the last lecture we have found the major result in this course, namely the Euler-Lagrange equations. So, let me just briefly mention what is the result. We have found that the extremal to the functional satisfies this second order ODE, which is my Euler-Lagrange equation. So, then in today's lecture I am going to look at some special cases. So, let me just categorize the different special cases in which this Euler-Lagrange equation simplifies. So, my first case would be where f depends, where my integrand to the functional depends only on y prime, right. So, in that case we will see how the Euler-Lagrange simplifies. In the second case we will look at the case when f depends, there is f has no explicit dependence, on x. Okay. So, we will see that f is only a function of y and y prime, right. And in the third case we will look at the scenario where f has no explicit dependence on y. Okay. So, in this case, for example, I have the form that f is only a function of y prime. In this case I have f is only a function of y and y prime, and finally in this case I have that f is only a function of has no explicit y dependence. So, it only depends on x and y prime. Okay. And then there is a special fourth case where f has a linear dependence on y prime, or I call this as the degenerate case. And why it is called the degenerate case, we are going to later on look at this situation. So, in this case my f has a linear dependence on y prime. Okay. So, let me now look at each of these cases one by one. So, let us look at the first case and how the Euler-Lagrange simplifies in this first case. So, as I said, in the first case my f is only a function of y prime. So, we see that my Euler-Lagrange equation. So, let me just rewrite the E-L equations. So, these are my E-L equations. We see that since f is not a function of y explicitly, in this case this particular partial derivative is 0, and then it's this equation shows that we can immediately integrate with respect to x to see that the result that we get is del partial of f with respect to y prime is a constant, right. Let us call this as c. So, in this case the Euler-Lagrange equation reduces to a first order ODE or differential equation. So, we could go one step further. We could say that, look, since f depends only on y prime, but y depends on x, right. So, we could possibly use chain rule. So, which means that so this equation is equivalent to saying that the x derivative of partial f partial y is 0, right. So, we could possibly use the chain rule to see that this is also equal to the second partial derivative of f with respect to y prime square times del y prime del x, right, and that is it. right. So, because f is only a function of y prime and this is set equal to 0. So, we see that we could have two choices. So, this means that we have f second derivative with respect to y prime times we see that this is y double prime is equal to 0. So, either so the product of this equal to 0 implies either this quantity is 0 or this quantity is 0, right. So, if this quantity is 0, it implies that f of y prime is a linear function, it is a linear function of y prime, right. So, that we can directly integrate f of y prime, directly integrate with respect to y prime twice, and we see that this is a linear function and this naturally reduces to case 4, which we will consider later. So, I am not going to consider the case where this is 0. So, which means we are only left with the fact that y prime, y double prime is 0, and in this case we get that y, the extremal y satisfies an equation of a straight line, right. So, C1x plus C2. So, we see that in this particular case the extremals are always straight lines, right, and we have seen some examples in this case. Let me just recap some of the examples. The example that we have seen earlier in our lecture was that of the geodesics on planes, right, and we saw that it naturally boils down to a straight line. Okay, so then let us continue our discussion on the second case. So, this case was very straightforward. So, our second case is when we have f is only a function of y and y prime. So, there is no explicit dependence of x on the integrand f, right, and we will see that in this case the Euler-Lagrange equation again reduces to first order differential equation, but it satisfies a particular identity, right, and in this case, so what I just said is the following. In this case the Euler-Lagrange equation reduces to the Beltrami identity, and let me just show what is that. So, it reduces to the Beltrami identity, right, and the identity is this particular function of y and y prime. So, the Beltrami identity says that this particular function which is given by y prime partial f partial y prime minus f is a constant, right. So, this is my Beltrami identity. Notice that the Beltrami identity is only a first order differential equation. So, it is a reduced order Euler-Lagrange equation. So, it is much simpler to solve than the original Euler-Lagrange equation. Okay. So, let me just state this result in this case in the form of a theorem. So, I am going to continue to number the theorem, starting from the first lecture onwards. We have so far shown one result in the form of one theorem, and so this is my second theorem. The first theorem was the Euler-Lagrange equation itself. So, the second theorem says that let us say we have a functional. So, let J be a functional, of the form J of y is equal to integral x0 to x1 f of y comma y prime dx, right, and we define our h, we define our function h of well, let me call this as 2 because let me call this relation as 2 because my 1, let me just be very methodical by saying that this was my relation 1 in the previous case. Okay. So, my relation 2 is this identity. So, let us define h of y prime as defined in 2, and we see that we see that the theorem says then H is constant, it is a constant along any extremal y, okay, and y is a function of x. So, all we have to show is that the derivative of this function with respect to x, which is the independent variable, is 0, and the result follows right away that the function will be a constant. Okay. So, the proof, as I said, is we have to show that the derivative of h is 0. So, let us see what happens. We figure out, we calculate the derivative of h. So, the derivative of h is, by definition, h is given by 2. So, this is the derivative of the following quantity with respect to x. We get that this is equal to del f del y prime minus f. Okay. So, then the next step is taking the necessary derivatives and using the product rule. We see that this is also equal to y double prime. So, taking the derivative of y prime with respect to x times partial f partial y prime plus y prime ddx of partial f partial y prime. So, that is the first quantity, and then we have the ordinary derivative of f with respect to x, that can be changed into a partial derivative of f with respect to the variables y and y prime, because those are the only two variables on which f is dependent on. So, then the other terms involve y prime del f del y plus y double prime del f del y prime. Okay. So, we will see that this quantity is nothing but the ordinary derivative of f with respect to x. So, all we have done is we have used chain rule. Now, notice that this particular quantity can be cancelled. So, this is in a bracket. So, we can cancel this quantity with this quantity and club whatever is remaining. We see that after clubbing whatever terms are remaining, we see that this is also equal to y prime ddx of del y del f del y prime minus del f del y, right. Notice that this is nothing but the Euler Lagrange equation. So, since I have, since y is an extremal, it implies that y satisfies the Euler Lagrange equation, right. That is what is our assumption to begin with, and that implies that this particular expression inside the bracket will be equal to 0, since this is the Euler Lagrange equation, the left hand side of the Euler Lagrange equation. Okay, and that completes our proof that h is a constant. Okay. So, we can see the power in this, the power of the result in this case. The Euler Lagrange equation has reduced to h, which is a first order differential equation, as opposed to a second order differential equation governed by Euler Lagrange equation. Okay. So, let us look at or revisit some of the cases, some of the examples in this second case. My first example this morning is on the case of catenary. Okay. So, we have looked at the problem of catenary, and recall that the functional involved in this case is as follows: integral from x0 to x1 y times square root of 1 plus y prime square times dx. Okay. So, we can see that the integrand in this case is purely a function of y and y prime. So, we can this very nicely fits with the second case. So, we can directly apply the Beltrami identity and set it equal to a constant. So, in this case, so we have to find the extremum, right. So, in this case the extremum will be satisfying the Beltrami identity, and we see that the Beltrami identity is given by, let me just rewrite the identity again. This is given by, this is equal to a constant. Let me call this as C1. So, just plugging in the value of, so this is my f. So, plugging in the values here, we see that after plugging in, we get the following expression y prime. So, I have just simplified a little bit, y prime 1 plus y prime square minus y times 1 plus y prime square. Okay. So, then let us then we can take a common denominator to see that this eventually, so this is equal to C1. So, this eventually reduces to the quantity y divided by 1 plus y prime square is equal to C1. Okay. So, that is what we have, and then the next step will involve solving for y by integrating this equation, and we let us continue doing that. Let us integrate this equation, and so when we do that, we see that, well, so the equation here is the following. So, when we do that, we see that, let me just first write in this expression, let me just separate out y prime and write y prime purely as a function of the other quantities y and C1. So, I have separated out y prime from the expression, and we can see that if that C1 cannot be 0, because C1 cannot be 0, right, because if C1 is 0, right, let us go back to the previous slide. If C1 is 0, the only solution I get is y is equal to 0, right. It implies that y identically equal to 0 is the only solution. Okay. Y identically 0 is the only solution, and that is what we have here. So, C1 is not 0, and then we can continue, we can integrate this to get the following, that my x is integral. So, dy by square root of y square by C1 square minus 1, here y prime is dy dx. So, I can integrate x with respect to y, and we get, so this is an indefinite integration, we get the following expression, C1 times log of y plus square root of y square minus C1 square divided by C1 plus C2, which is the second integration. So, then the next step will involve changing this particular expression. We have already now found the extremal, but the extremal is not in a form that I can show what is the shape of the curve in catenary. So, let me rewrite this solution in a more convenient form. So, first let us now write, rather than using the log form, let us write it in the exponential form. So, I see that this is, we see that in the exponential form I get C1 times x minus C2 divided by C1 of exponential, right. So, let me call this as exponential. Notice that I can take C2 on the other side, divide by C1, and that is a factor that I am getting, and this is also equal to y plus square root y square minus C1 square. So, let me call this expression as well, I call this expression as A, I call this expression as B, and then notice that I can always generate another expression from here. Let me just take the inverse on both sides. So, what I am saying is the following, we can rewrite expression B again as follows, that this is also equal to minus of x minus C2 divided by C1. This is also equal to 1 over this particular quantity, right, or no, sorry. So, C1 we have just multiplied by C1 throughout. So, this is C1 square divided by the quantity on the right hand side of B, right, and this is we leave it as it is. We call this another expression, let us say C, right. So, we see that, so why we have written another expression for B is because now the next step will involve adding these two quantities on the left hand side and the quantities on the right hand side. So, we see that the quantities on the left hand side will become, so this is e to the power x minus C2 by C1 plus e to the power minus x minus C2 by C1, right, and this is y plus square root y square minus C1 square plus C1 square divided by square root divided by y plus y square minus C1 square, right. And then we can simplify this further. This is also equal to, after simplification by taking the common denominator, this gives us this is equal to 2y, right, and the quantity on the left hand side is nothing but 2C1 times cos hyperbolic of x minus C2 by C1, right. So, finally, we get the expression as follows, we get the solution as follows. We see that my extremal satisfies this particular equation, y, so y of x is C1 cos hyperbolic x minus C2 divided by C1. So, this is a much more convenient form of expressing the extremal in this particular case. And if we recall, in this catenary problem, we are trying to minimize the potential energy of the cable. So, it turns out that if the potential and if the cable has this shape of a cos hyperbolic function, then the potential energy which was represented by the functional, the potential energy of the cable is minimum, right. Well, I am just saying minimum, we have not figured out whether it is minimum or maximum, but at least the potential energy has reached its extremum, right. Later on, when we talk about sufficient condition, we will show that this extremum is indeed the minimum. So, right now let us just assume that the extremum that we have found is the minimum. Okay. So, that completes the discussion of this example. Let me look at another case study or example that I have described in my first lecture, that is the example of brachistochrone. Okay. So, let me just revisit that problem. Okay. So, the problem involved a functional. So, I am not going to write the entire detail of this problem, but just the functional. The functional in this case involved an integral of the following form. It involved square root of 1 plus y prime square divided by square root divided by y dx. Notice that the quantity on the numerator is nothing but the arc length, and the quantity in the we had a square root y, and the quantity in the denominator represented a form of velocity, right. So, this is the total length divided by the total velocity. So, we are extremizing the time functional in this case. Again, notice that in this case also the integrand in this integral is purely a function of y and y prime. So, we can very safely use our Beltrami identity, and in this case my Beltrami identity will reduce the Euler-Lagrange as follows. So, what we see is that y prime del f del y prime minus f is, we just plug in this integrand. So, this is my small f, and this reduces to the following form y, so y prime square divided by square root of y plus y times 1 plus y prime square minus square root of 1 plus y prime square divided by y, and after simplification of this expression we see that this is also equal to negative 1 over y times 1 plus y prime square, and this is set equal to a constant by the Beltrami identity, okay, to get the extremal. So, from here we can solve for y as a function of x. The first step is to just invert this expression and take the square, right. So just for bookkeeping purpose, let me call this as C0, a constant C0, and now we invert this expression and take the square on both sides. We see that now the new expression becomes y times 1 plus y prime square. This is equal to another constant C1, right. I don't care, I don't want to simplify in terms of C0. Let me call this as another constant C1. So from here we see that the direct solution is not possible. The direct, so this is our extremal. The extremal curve satisfies this ODE, but the direct solution will not be possible. So we use an alternative approach. We solve this equation parametrically. So solve parametrically. So what I mean by solving parametrically is as follows. I am going to introduce a new parameter on which both y and x will depend. So I am going to explicitly find y as a function of that parameter and x as a function of that parameter, and that will describe the extremal. Okay. So let me just introduce the fact that let us say y prime is tan of psi. So as if y prime is the slope of a curve. So it is tan of psi. So psi is our new parameter. Okay. So immediately we can see that 1 plus y prime square is 1 plus tan psi square, which is secant square psi. Okay. So let me call this boxed expression as 1 and let me call this second expression as 2. So I can directly plug in this quantity here in the boxed expression, and we get that so from 1 and 2 I get that y is equal to C1 divided by secant square psi, or this is also equal to C1 cos square psi. So I have already found the parametric representation of y with respect to the parameter psi. So let me also call this expression as A, and now my next task is to find the expression for the x component in the form as a function of the same parameter psi. So to do that, let us notice the fact that so let me rewrite. So y is C1 cos square psi, that is what we have found, and let me further simplify this using the double angle formula, that this is also equal to 2 times 1 plus cos 2 psi. Okay. So now to figure out the expression for x as a function of psi, let us first differentiate this expression with respect to psi again. So we see that dy d psi is equal to negative 8 C1 cos psi sin psi d psi, right. So dy d psi is this, or let me just say the following. Let me just say that I am going to take this element d psi. I am going to take this element d psi on the right hand side, and I can express dy, the element dy, in the form of this quantity times d psi. Okay. So then I also had that recall that y prime was tan psi. That is what we began with, or from here I can see that dx dy is 1 over tan psi, or this is also equal to cotangent of psi, or what I see is that dx is equal to cot psi times dy, and the next step will involve just explicitly substituting this element dy with this expression above, and we see, and then integrating with respect to psi. To finally get that, let me just rewrite now after substituting this expression. First we get that dx is negative 4 C1 times 1 plus cos 2 psi d psi. Okay. And then the next step will involve integrating this expression with respect to psi, and we see that x of psi is another constant C2, which is a constant of integration, minus 2 C1 times 2 psi plus sin 2 psi, right. And let me call this as B. So just a moment, we have now named this expression as A, because this is the relation of y with respect to psi, and now we have renamed another relation B, which is x as a function of psi. So now we have completely described our extremal motion x and y in the form of the parameter psi. Now students should recall that we had already revealed the solution to this problem, the Brachistochrone problem, and we had a similar, I had written a similar solution, except that instead of 2 psi we had psi. So you can just replace 2 psi by psi everywhere. And if people recall, if we were to plot x versus y, the plots will follow a locus which is a point on the rim of a bicycle wheel, right. So these are nothing but this locus of points are nothing but following the curve which is known as the cycloid, or a point which lies on the rim of a bicycle wheel. Okay. So that completes the discussion on this example. Let me just move on